everyone can hear me well. Thank you very much for this nice introduction. I put the things that you said on the next slide. Today we will talk about quality assessment of PV systems by analysis of system performance. I go forward. You see my picture. I'm a PhD since many years. I've been working on photovoltaics for about 30 years. I started with cell development, as maybe many people do, and I now work on performance analysis of modules and systems in our university, and also with particular emphasis sometimes not too much on luminescent solar concentrators, which I will not talk about today. The work that I will be presenting is part of the International Energy Agency Photovoltaic Power Systems Program. I would like to present you briefly what this program is about. Presently, we have 29 members of 24 countries in the program, and activities are carried out in a collaborative way on a country basis, and every country selects one or two experts that represent their country, and they work together on technical and non-technical subjects. The work is divided in tasks, and currently we have about 8 tasks active. You can find all information on this website indicated on the bottom. The present IEA-PVPS tasks are the following. We have 16 tasks, of which a number of tasks are active and some have been closed, as you can see in the dates. We will talk now about so-called task 13 in red. This is on photovoltaic performance, quality and reliability. It has been up since 2011, but it has been extended recently to include new year data and new partners, and it will end by 2017. The relevant PVS issues of this task are related to business models. That will be one of our subtasks, and we focus on quality and reliability, as you can see in red. The subtasks of the task are defined here. It is about the first subtask number 1 is on economics of PV system performance and reliability, where bankability is an important issue. I will not talk about that today. The subtask 2 is on system performance and analysis, and that's the topic of the webinar today. The items that will be discussed are data that have been acquired and analyzed in the past years. Subtask 3 is on module characterization and reliability. For example, how snail trails are progressing in the field, yellowing of modules. That's the subject of this subtask. And of course, everything should be disseminated in a proper way, and that's subtask 4. So today in our webinar we will talk about quality assessment of PV systems, and as Fernando already introduced, it can only be properly performed if you have data, and that's a really critical issue. Many data is out there in the field, many systems are out there, but data is something that people are reluctant to share sometimes. In the task 13, with all the member countries and experts available, we try to find detailed data on selected PV systems which are well monitored across the world, and these will be put in a database for everyone to look at, to compare data and so on, to even benchmark perhaps their own system with the data that's in the database. The second approach is to do a statistical analysis of really large amounts of data, and in that sense only 2 parameters are relevant for the performance, that is annual yield and the performance ratio. The details of this webinar and the data can be found in the recent report here. You can see it here, which you can download from the PVPS website. Well, I will talk about shortly. I will talk about the motivation of this work, and then we'll talk about the performance database, which is essentially a small sample of data. A statistical analysis, which is a large sample of data, or at least a large enough sample. And I will briefly discuss, if time allows, something about the Counting the Sun campaign, which we had in the Netherlands in the past 2 years. And of course, I should conclude with some remarks. The motivation is clear. We know all, hopefully all the people that are attending now, they know that PV is becoming a mainstream energy harvesting option. You can see in the picture down here, this is a so-called IEA-PVPS snapshot, what's happening in the world. we have about 177 gigawatt installed capacity of PV in the world, which is about 1% of the global electricity production already, but we can also say it's only 1% and we still have a long way to go. Of course, if we install these amounts of capacity, we need to have optimal performance is required. We cannot accept performance that is limited by whatever reason, because otherwise PV will not become a mainstream option in the end. So it is all about optimal performance, and that's we try to find in this task. So we need to know how well is PV serving the world. Is the performance really optimal? And do good promises lead to good performance? So if you want to install a PV system, say the installer will at some point tell you how much will be the expected annual yield, which is a promise based on solid knowledge, I hope, but is this really guaranteed? So high performance is linked, actually is equal sort of to quality. High quality gives you high performance usually. But of course, without data we cannot address performance issues at all, so we need data. And then again, if we have all this data and if we have all these systems scattered around the world, we try to find a link with their performance parameters with the climate zones in which they are. This is an example of an accepted map of climate zones. You can see different colors here down here, which designate different kinds of climates scattered around the globe. You can see red areas here and here, which is, as you can see, desert areas, also a little bit here in the west. Those hot and dry climates will have a different influence on the PV modules than, for example, here in the Northwest Europe. And we still have not enough data to see properly what is the link with the climate zone and the PV system performance itself. So this is one of the issues that we are now pursuing in this task 13. Pardon. Another point is, if we are going to include PV systems in the world, they will not always be located in an optimal situation. And these are just a few examples. We have, of course, in this case, palm trees and a facade. This facade in itself is already not optimal located. The shading of the palm trees, of course, lowers the performance. If you look here on the top, you can see a picture which I downloaded from a Dutch installer site, and I would be ashamed to sell a system like this because it's inherently suffering from shade. Then this is a example of a dormer window, which in the morning, certainly in this case in the northern hemisphere, is casting some shade on one or two panels, and this will influence, of course, the performance. Here on this side here we see not a good panel, but you can see the effect of shade on the IV curve. This is the sort of correct curve, although it has very high series resistance. If part of the module is shaded, then you can see strange effect in the IV curve, and then it really depends on the inverter if it finds the proper maximum power point of this whole curve or not. So shade is one reason, certainly in the residential area, for lower performance. But then monitoring data, what are we going to measure and what are we actually going to communicate? First of all, we have the sun and the irradiation. This is going towards the PV array, which is functioning in a certain ambient temperature. We then have a module temperature. We have even some wind speed sometime. The PV array is producing DC power and voltage and current. It's then inverted by the inverter to a AC power, and then it's fed into the grid. In all these steps, we have losses from here to here to here to here. We start with a reference yield. We have then an array yield, including already some losses here. Other system losses will then cause you to get the final system yield. And this picture is made by Achim Moite from 3E, and this is the basis for another report in the IEA Task 13 on how you would do analytical monitoring and what you can do in detail, how to find issues regarding lower performance. For a residential system owner, this whole system is way too complex. He or she is only interested in the final system yield, or perhaps even only in the economical benefits. So there must be a way to translate this kind of data or parameters to a simple figure for the customer on an annual basis. So the task 13 field performance analysis is about twofold approaches. It's an analytical approach. So we collect and analyze validated data sets from all partners. We collect them and put them into a public database from which you, for example, could see and analyze the monthly performance ratio. We also have a statistical approach. This is more on collecting huge amounts of system data from all participants. And if that's not available, we can also try to use so-called web scraping techniques, which is followed by some analyses. And I come back to that in more detail later on in the talk. So our performance database looks a bit complex, but I can explain what is happening here. We have a central database here, and Thomas Nordman from TNC has designed a so-called input tool, which is based on FileMaker. There's a certain way to introduce your system data, which is well validated. You know exactly when data is there, when it is not there, and how much is fed into the grid and whatnot, and so on. This is all taken care of in this input tool. This input tool is then sent to our operator here, who is analyzing all the data. There is important quality control step there, also from internal people in the task 13. Then it will be put into a master database, and through the web interface you can have, as a user, direct access to, with a browser, to all the numeric info on plants, system, monitoring years, etc. And you can design your own graphic information, but you can also export that data into an Excel sheet, for example, so that you can do your own analysis or benchmarking with your own systems. Go to the next slide. This is an example of this input tool. It is an example for, you can see Switzerland there, here. It has 5 items basically. This is general information, and you can go to project, inverter array, and operational data, and that's the way to input all the data. And if it's correct, you have to validate it. So of course, it will then in the end be sent to the database, and you can use it yourself. This is an example of what's the status now. You can see geographically it's spread over well, the US and Europe basically at this point, and a database is never full enough, you might say. So we really want to have more and more data, which is necessary to compare the system performances in different areas, and specifically in climate zone differences, to see that. Presently, this is a plot of what we have. This is, you can see on the left, down left, the number of years from 92 to 2014. These earlier data are from the so-called task 2, which was already running quite a bit of years ago. Now you can see in the task 13, people have given more and more data. So this is the number of systems and number of years of data that's available for several countries that are participating in the task. There's still some countries pending with data, like my own country actually, Australia, Italy and Germany, and there will be some others as well. The point is clear. You need to have a system which is properly monitored with also proper irradiance sensors there, so that you can correctly measure or determine the performance ratio of that system on a monthly basis. This is an example of the automated analysis in the database. You can see, for example, the green line as a function of month here gives you the performance ratio of the particular system, and it's maybe hard to see. It's difficult to see actually what the number is. It's between 0.9 and 0.8, which is actually a very good system. You can see that in blue is the final yield per month. In yellow there's some losses and in capturing, and in green there's another system losses. So in this way you can see what's happening in your system. In red line here it says the outage fraction, so how much of the time of that month the system is not running properly, or at least there is no data. That's always difficult to say if it's not running or there's no data. This is one example. If you go further with analysis like this, you take on the left side, you take the early data, for example. So you plot the reference yield, the final yield versus the reference yield. If you and you see the blue line is the one line, the linear slope with slope 1. The systems have quite lower slope in there. The performance ratio 0.75 is this line here, and you can see that some of the systems do have that performance ratio, with many are much lower. The same plot, you can make that for 2005 to 2012 years, and you can see clearly by comparing that the performance ratio have been increasing even towards 1 on a monthly basis. That's possible, but high. That is actually very high. But clearly the point you should take from this is that the performance ratio is improving. Now, and we're going to skip this one. Sorry. If we, I was going to work further on the performance ratio. This is another way of showing that data. It's actually the same source. It's the PVPS Task13 database. You can see the average is slowly increasing, but it's around 0.7, up from 1990 to about 2004. This is from the whole database, from all systems in the world. This is an example here from a German system, or systems in Germany, sorry, where the 1994 data is shown here. And so that's data from systems which are installed in 1994. In systems installed in 2010, you can see clearly that the performance ratio is much better and even approaching 90%. And in this particular paper by Niels Reich, myself and others, it is stated that 90% or perhaps 92% may be the maximum performance ratio that we can attain in this area here. Point is, do you want to contribute? We are always seeking more data. And so the requirements of that data would be that it's a validated operational system data. We should use the input tool that will be provided to you. If you're interested, you can always mail me. But as we are part of the IEA-PVPS task, it officially should be done through your country representative or your EXCO member, it's called in this way. But for any information, you can certainly mail me and I'll provide you more data or information how to contribute. You can always be an observer in our meetings. We have every 6 months we have a meeting somewhere in the world, and if you're interested, you can always attend as an observer one of those meetings. I now continue with the second part on statistical analysis. I have shown you that performance has been increasing in the past decades, but still reasons for lower performance than expected or promised, I come back to that, are sometimes difficult to detect. Especially in the residential systems where you may have shade. Monitoring is relatively very expensive and people are not doing it or in a very insufficient way. And if they have monitored data, they do not know, the customer doesn't know whether this is the correct amount of energy that has been generated or not. So per country or region in a country of the IEA member states, we want to have a large amount of systems. So we divided the data in a system size bin of about a factor of 10, so lower than 1 kilowatt to 10, 1 to 10 to 10 to 100 and so on, up to 10 megawatt peak, because we want to investigate the system size differences. And we ask the annual yield for a sample of systems in a region or country, which is the kilowatt hours per year per installed kilowatt peak as a function of that location and climate zone. We can link that up with the map I showed earlier. I also want to have there an annual average performance ratio. Sorry. And this should be determined by using local sensors or satellite data, or at least the one that is supplying the data from the country should do all those measurements and calculations, so that in the end we at the IEA are not interfering with any privacy matters that may be there. We just want to have the average annual yield, the average performance ratio of a certain region linked to the system size. And if we have enough data in terms of years, we can try to find the degradation rate of the systems out there in the field. We focus here on annual data because that is what the customer really needs to know. And the customer can be a residential person, but also a larger customer, of course. I have an example for data from Italy from the past years. Francesca Tilli is a representative of the country Italy. She has supplied me some data. She decided herself to divide the data in a north, central and south division. Let me go a little bit deeper here. In black you see the data from the north, in red the central, in blue the south. For 2008 to 12, you can clearly see that the central and southern data are very similar, and then the northern data is quite a bit lower, quite about an amount lower than the central and south data. Going into detail, for example, if you look at the performance ratios, the central is very high, 0.82, while the south is lower, 0.77. And you need to have more detailed information on what's happening there to see why this is so. At least in this exercise, it was found that one of those systems actually was not performing well, which had influenced this southern performance ratio. And although people have experienced losses economically, they do not seem to handle these problems with performance properly. Now, if I average all years, you can see it's not. You can see also that the number of systems is not that much, but a large enough sample size, I would say. If you check the annual yield here for all the years together, and you see that for the system size, you can see that the larger systems in general perform better than the smaller systems, and I guess this has to do, of course, with the better management of a larger system than a smaller system here. Another way, because in our past years we have found it is very difficult sometimes to get the data from the countries, then we try to find another way, and this is presented here, which is called what we call data mining. And you may all know that, for example, SolarLog, just an example, there are many out there as well, show system data of some of systems for smaller systems, larger systems. And you can see typically a picture, some system data, description, and, for example, a daily energy yield for this particular system, and clearly showing there's some issues there with clouds in this particular case. Well, we want to analyze that data, and this is why we developed a technique which is called web scraping, or actually we applied it, it's known already. So what you do is the following. You can see this information here. You could copy it in a simple way to a sort of database. And copy and paste in a database is done automatically in a Python script that we developed. So the point is, the question was, is it legal or not? Well, people have SolarLog systems, and they have flagged that their data can be public. So as the data is public, we can really extract. So that's, in my view, legal. The point is clearly, what is the accuracy of the data? Because we do not know at all how the energy or power that is measured of the system, how this is measured. It can be the output from an inverter. It can be, of course, really a kilowatt-hour meter or something, but we don't know. It certainly is not known in these kind of systems. So this, of course, is a problem, but we assume that we have a very large sample set, so accuracy is hopefully not a problem because we have this large sample set. This is an example here for 5 countries. We have, well, you can see about 700 to 500 systems in this particular example for these countries. You can see system size differences. Belgium has 6.5 in this sample, kilowatt peak. Germany 15 kilowatt peak. And you can see, interestingly, that, for example, if you find the distinction between polycrystalline material panels and monocrystalline materials and amorphous, you can see that in Italy there's many polycrystallines, like in the Netherlands, but in France it's the other way around. And in Belgium and Germany, you can see that poly and monocrystalline have about the same market share. This is just simple data that you can extract from the database. If you look into the annual yield, you can see for the Netherlands, Germany, Belgium, Italy, and France, that the annual yields are varying a little bit. for a strange reason they are going down, but if you look in 2014 data, they're going up again, so it clearly is linked to the irradiation values. What you also see and what you expect is that the Netherlands and Belgium are similar. Germany is a little bit higher than the Netherlands and Belgium, then France, and then Italy is the highest yields, and because of the more southern location of the country, of course. And we have also analyzed that in a region way. For example, if you look in this graph, you can see in green the northern part of France, Germany, and Italy, and in red the southern part. And if you find the annual yields there, you clearly can see that the southern part has a higher performance of between 6 and 18% higher. Certainly the highest differences are in Italy because it's a larger country there. So this is just a way to show differences in performance in annual yields over a country. Even in the Netherlands, so although it's very, very small, but if you look at the irradiation variation map, it's clearly on the coastal areas the irradiation is the highest in the Netherlands compared to the inlands. Well, if you check the annual yields for systems that are here, you can clearly see that the yield is also higher. And in this particular example, it's about nearly 8% higher in the coastal area than in the inland area. Also, the performance ratio is a little bit higher. That may have to do with the fact that at the same time that irradiation values are higher, usually temperatures are a little bit lower here, and that increases the performance ratio. But a more detailed study should give a definite answer there. You can also plot the distributions of annual yield for 2014 in this case. If you go, you can see the distributions here. The line here gives you the 1000 kilowatt hours per kilowatt peak line. Of course, going from the north to the south, you can see clearly that Italy have a better performance than the Netherlands, for example. You can see from the scatter that the Italy sample is smaller than the Netherlands sample and the German sample. And this was presented this spring at the IEA-PVPS IEEE-PVPS 42nd meeting in the US. What we also presented there is the TRS mapping. So we used the geographical information systems schematics to map the yield. We know all from the solar log, we know all the locations of the systems, for example here in the Netherlands, and we can map those yields and of course interpolate between them to color code the annual yields in this way. And this is the legend there. Note the legends are different for every country. So this is Netherlands, Germany, and Italy. You can see there's a large cluster of samples in the south of Germany here, and in the north of Italy here, and in the Netherlands it's quite a bit scattered over there. Clearly, the Netherlands it's similar for all systems. You can also see that the coastal areas are not performing better as compared to the inland systems, and there are only a few, so that probably is the reason why you don't see that better performance. In Germany, it's very hard to see due to the fact that we have many systems there, but the southern part gives you a better yield than the northern part. Interestingly, the blue things here are low yields, and we have to really go into details if one of these systems, like here or there, if that's the only one system or a few systems are not properly functioning there, causing a blue color, so a low yield. But you can also say this is an interesting way of showing where low yields are in the country. And if it's tiny spots like these, it means that probably one of those systems are not functioning well, so we have to look into that in more detail. You can see in Italy that the more south you go, the performance yield is better than in the north. With that in mind, we are trying to map the whole of Europe, and this is a strange picture of Europe. You see, for example, you miss Spain here, but it's all the countries that we have data for. The gray areas in France, that is areas that we do not have data for. And what you expect is clear: a low yield in Scotland going to high yield in Greece. And this is ongoing because we are scraping more and more systems as we speak. Now this provides a link with the climate zones that we still have to do. If you remember the first graph of the climate zones, this was one climate zone basically. So even within the climate zone there is differences, but well, we can only talk about climate zone relations if we have enough data for the other climate zones as well. So this is work that is ongoing in the task. Another example, which is links to the Netherlands. We wanted to find how the performance is going on in the Netherlands itself and how people are seeing the performance. So we have this, we organized a so-called awareness campaign. How well is my system doing, which is part of what we call the Dutch Solar Days. And what we did was measure 1 week only the yield of many systems. We used social media, but we got into a national television show, which is a national network. We had 1 million viewers, and this led to 5,000 systems that people volunteered the data of, spread all over the country, and they were asked just to specify their system details and measure the weekly yield. Now, what you then get, this is the distribution of weekly yield. First of all, you can see it's quite broad. It has an average of 33.4 kilowatt-hours per kilowatt peak, and of course there are many reasons for that. We know all the orientations and tilts of those systems. We know the PV panels type, module type, model type and inverter type. So we can mostly explain why it's so broad. Then again, there's quite a bit of very low yield, and this may be caused by problems in the systems. And we have reported for every system, we gave an individual report back to the customer, and many have solved their issues with string inverters partly broke and so on. Many small errors that have been repaired, and that's a good thing of raising awareness. What we see, actually most of the systems are performing well. The average performance ratio was 0.74, which is quite low if you compare the data that I just showed earlier, where it was on average like 80, 85 or so. We see in this particular week, note it's only 1 week, of course, we see irradiation differences about 30% in that particular week between coast and inland area. There's also similar, of course, for yield, which is much higher here than here. And the performance ratio, this notably, is roughly the same over whole of the country. That's good. That's a good sign. We also asked if participants had problems with shading, for example, and this, well, some of them, 10% of those participants, they have indicated that they have some form of shade. If you then calculate the performance ratio of that particular set of samples, you arrive at 0.7, so a little bit lower than the average of the whole sample. Now, in conclusion, it is clear, if you want to say something about performance, you need to have data. And performance is equal to quality. That's our statement, which can also be questioned, of course. We have seen over the sample sizes that we have investigated that the system performance is increasing. However, the last example I showed from the Netherlands, it's only a weekly performance ratio, I know, but still the practical example shows that it may be otherwise. And actually, if you have more and more systems installed in a residential area, you may expect that performance ratio is not 0.9, but lower, but due to the fact that the systems are not installed properly. And more, even worse probably, the shade is interfering there. We still have to link with the climate zones, and we need a lot of data there. And the point is also that if we have that link established, we will discuss the findings with the Standard Development Committee, IEC, the International Electrotechnical Committee, specifically the TC82. So maybe some of the standards must be modified. For example, if you are in a hot and humid climate, then the standard test for lifetime test, for example, for PV modules may be changed, may be modified, and maybe you have to define, say, a different standard for different climates. But this is very speculative at this point. So reliability, the question, I would say this is a continuously high performance ratio. But to do that, of course, you need data and monitoring data. So in our task, we still are collecting and analyzing data. We use participants to supply us data, and we do statistical analysis using now web scraping, but hopefully we get more data properly modeled data from countries that participate. For the calculation of performance ratio, we need irradiation data, and perhaps the JRC or the people there that have data, irradiation data over Europe, for example, are able to supply that so we can properly determine the performance ratio. Note, of course, there's inaccuracies related to satellite data, for example, related to irradiation, but we have to deal with it. So if you're interested, please join or contribute in some way using your data, or just supplying, for example, a website that you could scrape, and we can analyze all that data, and publish it in some way. So I would like to thank you for listening. We are now entering the Q&A session, and I'd like to show you the last slide, which gives you reports that are now have been published by the IEA-PVPS Task13. You can find it on this website. I've been talking about the report number 5 here, analysis of long-term performance of PV systems, but the other report, analytical monitoring with connected PV systems, is also very well material to read. Those are linked and indicated in red here. So with that, I'd like to close my webinar and open the Q&A session.